Good morning. Today, I will present our joint work between Pennsylvania State University and Kimberly-Clark Latin America. This is a success story where I will highlight 3 achievements: the creation of OR capabilities inside our organization in Latin America; second, a joint project between a university and the company; and third, the creation of MIP to solve large scheduling problems in a very complex environment where we have dynamic changes and a lot of challenges that we will discuss later. This is the agenda of our presentation. First, I will give you an introduction on the environment in which this project was created and the OR capabilities and the partnership we have developed with Penn State University. I will give you an overview of the optimization model and also the heuristics we are using to try to improve the speed at which it works. SPN is the graphical user interface with which the planners interact with the model. And finally, I will give some results and impact on the model and some concluding remarks. Kimberly-Clark Corporation is a large multinational company with presence in many countries and with well-known brands like Huggies, Scott, Kleenex that probably many of you have used at home. These are some of the figures related to our company. Kimberly-Clark Latin America encompasses all countries south of Mexico. Mexico is not included. This is a region that has seen quite a large growth in recent years, and so is growing our business over there. And it's also quite complex region. There are, for example, the traditional trade and the modern trade are both very important. This means we have to sell to customers like large supermarket chains, which will be very much what you have here in the United States, but also we have to sell to about 1 million very small mom-and-pop stores. And the customers that go to those different scenarios are different. So our products have to be customized to different niches of markets, different income. That will have an implication on the scheduling, as we are going to see later. Also keep in mind, infrastructure is low. The moving products from countries to countries inside the region can be quite challenging. Even inside the same country, it might be difficult. In Brazil, when you ship something from Sao Paulo up to Manaus, it can be up to 12 days because the shipment has to go by car, or by truck, then by boat, then getting by truck. So, in order to face all these challenges, our leadership considered that operations research is a very important thing to have in our business. We want our leaders to be taking decisions based on analytic tools and not only gut feeling. Therefore, we have been trying to increase the presence of OR in many parts of the business. That's how 6 years ago they created the Operations Research and Analytics group, to which I belong. These are some of the activities we do in OR and analytics. We have been able to develop many interesting projects in various fields that support all the operation, not only supply chain, but also in some areas of commercial operation. And also, we have initiated partnerships with top universities, like it is the one that we have with Penn State University. This has been a very fruitful partnership. We have had many projects, including this one I'm going to talk today. And during this time, we have had people coming between both organizations. Interns, students coming from Penn State that have joined the operation in Kimberly-Clark, and also Kimberly-Clark employees that have gone to complete the graduate studies at Penn State. This is the team that has been directly involved in the development of this project. Actually, there's a lot more people that I'm not mentioning here. These are the main developers of the model, but in the part of implementation, we have had a lot of people. Even in the development, people who were before I even joined the company were already working on this project. As you can see, we are spread all over the region. Now, to talk you more about the complexities we face in Latin America and the challenges for our business, I will give you with Gustavo Palacios, Supply Chain Director for the Andean region. the view is not. Okay.
Business competition has tremendously increased during the last years. Then, to be successful, it is necessary to satisfy customer needs and offer good service in an environment full of promotional activity. Those demands stress the planning process and increase the risk of obsolescence due to frequent product changes. All these factors affect working capital, product costs, and erode business results. The traditional planning was not effective to solve this puzzle, due to the large amount of information and the short period of time available for a quick response. With the models developed by our operational research team, it was possible to create a program to put all these restrictions together, to optimize the use of our resources while achieving the best cost equation. After some months of getting confidence, aligning the teams, and stressing the model to real scenarios, we found that service level increased, inventory dropped, and productivity improved. The tool is offering a good combination of productivity and flexibility. It has shown to be effective in other businesses and markets, therefore we have defined it as the standard tool for planning in our company in Latin America.
So we'll present some of the details of how the model works. Far away, so most of the plants have to do many products at the same time. Now, changing the machine to do product A to do product B can be quite cumbersome and complex. They have to stop the machine and practically disassemble and assemble it again. This can take up to 7-8 hours. A lot of people is involved. Last time I saw one of those, there were 13 people involved, and changing from A to B is not the same as changing from B to A as far as time and cost is concerned. That's what we call the sequence-dependent setups, and it poses an important complication in the mathematical point of view. Also, we have to take into account the machine capabilities. We cannot assume, as in many theoretical models, that the machines are identical, because they are not. We have acquired these machines at different points in time with different technologies, so not all machines can do all the products in the plants. And finally, we have a non-stationary demand. Of course, the final demand for diapers, for toilet paper is fairly stable, because the consumers don't use more in December than January. However, because of the commercial situation and the negotiations we have with our customers and clients, we can have end-of-month peaks. Also, there's a lot of very aggressive competitors doing a lot of promotions, and so are we. So because of the promotions, then you have to change the SKUs that you make from one month to the next month quite frequently. Similar problems to ours have been attacked in the literature. These are only a few of the papers we found and checked. Our approach is closest to Denton and Woosley. Here the papers are classified according to the solution technique, problem modeling, and also some of the industrial applications we are aware of. Now we go into the model itself. These are the inputs and the main outputs of the model. I'm going to comment about some of the inputs. Most of the data is gathered automatically from our ERP system and fed into our system. However, some of this needs some additional thought or consideration. In particularly, the target inventories at the end of the week and at the end of the planning period have to be very carefully thought about. Basically, what you want with the target inventory is to have enough inventory for the next month until the production is programmed again. But as you can see, inventory and scheduling are related, and it's hard to know which one has to be made before, because since we are planning for this month, we don't know anything what's going to happen the next month. So we need some a priori idea of how this is obtained. The safety stocks are actually computed with a variation of the order up to level formula, and you can see actually tomorrow, Daniel Silva, who is here, will give a presentation, session WA12. And the relationship between the inventory and scheduling, we also have been studying that. Daniel Sanchez, who is seated over there, did that in his master's thesis in a university in Bogota, Colombia. Also, setup, cost, and times come from the plant, and they are basically based on the waste generated at the startup, the cost, I mean. And the weekly forecast come from a sales and operation planning. They come with a number for the month, not for each week. So we split the number in 4 weeks according to historical data. But the planner has the option to override that if he wants that specific production to be in week number 2, to week number 3, etc. I will explain the questions of the model. So the first one is the traditional inventory balance equations that tell you that the inventory at the end of the week is what you had before, plus the production minus the sales. These equations tell you that the demand is split either in sales or an increase or decrease in back orders. These equations define the net inventory on the left is equal to the target inventory, I tilde on the right, plus or minus underage and overage variables. The purpose of this equation is to define the I minus variable that you penalize in the objective function when you don't fulfill the target, so that it's not a hard constraint in case there's not enough capacity. Now, the sequence representation in the model needs some specific thought. Here, in this example, we have 3 weeks, T1, T2, and T3, and we are assuming we are only making 3 possible products. Not all products are made every week, but in principle, all of them could be made. We have an I naught node on the left that represents the product for which the machine is set up right now. So if at the end of the planning period, of the previous planning period, they were making product a specific number 2, then that will be 2. And the last node, 0, is just a dummy node. So with this, we have transitions inside the same week, within the week, and we have transitions between 1 week and the next week in green. Each of those will have binary variables called deltas within the week, gammas between 1 week and the next week. And basically finding a production plan is the same as finding a path along this graph like this one that we have over here. So that will be a valid production, and there were additional equations we will show in a minute, but we are going to have a flow constraint that says that everything that comes in to every node is equal to everything that is and gammas that go out. That is 0 or 1 depending on whether that machine is used or not, and that defines the variable y. We need time constraint. The systems are capacitated, so the total time is time used for setups and time used for production. That's the use time, and is bounded by the available time for that particular week. Each week might be different because you can have plant outages on a particular machine. Plus, since we divide every month in 4 weeks, then not all 4 weeks end up having exactly 7 days. The user can fix also a minimum batch. We have to be a little bit careful here because the minimum batch is not for the week, it's for the whole run. And a batch, can be split between 1 week, or can be only 1 week, or split within 2 or more weeks. So these equations tell you that the quantity X is at least L, which is the batch size, and a binary variable that is Y is 1 if the product is made in that week. Both gammas will be 0 if that product is made only in that particular week. If one of the gammas is 1, that means that the product is split between the previous or the next week, and this equation gets disabled, but it will enable this equation that says the total batch between 2 weeks is going to be at least this 1. The minimum batch usually is small enough that 2 weeks should be plenty. But if it were not, then you will have new equations for 3, 4, etc. The same type of modeling would be needed. Finally, you can think of this problem as a series of traveling salesman problems interconnected. And as it is the case in the TSP, you have to prevent existence of subtours. This equation should be quite familiar to people who have studied a TSP. And basically, what it says assigns ranks to each product used in a particular sequence in the week, so that if delta ij is equal 1, so if you make a setup free between I and j, the ranks between I and j must differ at least in 1. If the product is not used, or if delta ij is 0, then the equations get disabled and the ranks become irrelevant. And finally, we have an objective function that tell you that you have an income coming from sales and costs associated with setup, holding, production. Sorry about that. Something I wanted to point out is, for clarity purposes, I am representing only one stock location here, which we assume is close to the plant. But our general model allows for multiple stock locations with lead times and transportation between them. It's just more cumbersome to describe. Now, that model, as I have presented, can be coded in a commercial software, which we did, and start running for some instances. So originally we started with a 4-machine feminine plant, and it was okay. There was a plant in Colombia, around 80 SKUs, although they were growing later. And in a few minutes we were able to get answers, so that was quite satisfactory. However, when we started to move to other plants with more machines, with more SKUs, then we run into trouble. The same model would not work anymore because of the combinatorial nature of the formulation, of the problem itself. Even some plants with the same number of machines and SKUs, just changing a little bit the parameters could mean the difference between getting or not getting any solution in a reasonable time. As you can see, for the big instance, after 30 minutes, we were not getting any type of solution. The gap was still too high, 53%. It might be the case that was already the optimal solution, but the system had a hard time trying to prove that that was the solution. So when we saw this, we decided to try heuristics to help improve the speed of the solution. We tried many things, and today I'm going to present 3 of them, 3 of the heuristics used. The first is the one we call the assignment model. Basically, what it does is try to assign the most optimal way products to machines. Okay? The assignment model is just the model I presented before, but ignoring all the questions that have to do with the sequencing. Okay? So this representation is not very accurate because the time is not involved. The assignment model does have the time and the inventory balance equations, but just to give you an idea, we are going to have some demand, some flow cost that assigns SKUs to machine, and some capacities for each machine on each week. So we solve an LP, that's done very quickly, and some of the capabilities will be eliminated. The planning result for this model is not particularly useful. Basically, since it is ignoring all the setup times, it will try to do more SKUs than is acceptable on every week, and it will have no time left for setups. So we don't use this to run an actual production plan. However, we just try to use the ones that have a positive assignment here and redefine the capabilities. So probably before, if you see here, for example, machine 2 could do 3 SKUs. After the assignment is run, we only have 1. Okay? So we go back to the original problem, redefine the capabilities, and say, okay, now machine 2 is going to be able to do product 3 and not all the others. Okay? We know that this pre-assignment has already selected the most profitable machines, so we expect not to change dramatically in the results, but we will have a smaller problem. The second strategy is a little bit more aggressive because what we are going to do is to eliminate some of the transitions. So originally, imagine you have 6 products. They are not here in order, and it will be clear why in a few minutes. And in principle, these 6 products that can be made on a machine, you can make a transition between any product between these 6. So all these transitions are available. However, there is an optimal sequence. If you had plenty of inventory, and you don't have to worry about that, but only worry about what is optimal from the plant point of view, what you do is that you solve a traveling salesman problem using as a city each of the products and as a distance the cost to make a transition between I and J. And in this case, I am assuming that the TSP, conveniently enough, is this circuit around the nodes. Okay? So it will be, if you have plenty of inventory, this will be the sequence the plant will follow. They will love to do this, never change the machines. However, in real life, all of a sudden, when you're doing the planning, you are very low on some particular product, very low in inventory. So you have to break the sequence and try to do that one. So we are not going to stick to this sequence. We are not going to force the system to do this sequence. However, we are going to give it a little liberty to move close around this sequence. To better define what I mean by close, I need to define a cyclic distance here. So for example, along the TSP path, this distance between 1 and 2 is 3 here, and between 6 and 1 is 2. The strategy says, okay, let's fix a maximum distance, in this example is 2, and keep only those arcs for those that the distance is at most the maximum distance. So we had all this, and after we remove it, we are left with a lot less arcs, as you can see here. Okay? So we are not forcing the system to take the optimal path, but something close enough. And we are eliminating some transitions that probably will never be made on the plant. By the way, we had to collect all the data to every possible pair of SKUs, and that was very hard because, of course, there were some combinations of setups that they have never been performed. So they were just estimates. Well, we will never do this, but if we were to do it, probably it will take us about this time. Now I will show you the impact of this algorithm. Of course, we are not getting the optimal solution because we are changing the problem. We redefined the arcs. We went back to the original problem with different set of arcs, a lot less binary variables. And what you see here is the blue line is the solution. Well, let me start here. This one, this point here, right top, is the optimal solution. This was a small model, so we were able to get the optimal solution. And we reduced the number of arcs, the percentage of arcs, that's on the x-axis, and for each of those computed the solution time and computed the optimal, the value of the objective function attained. And we run it many times so that we could average the solution time. And what this teaches us is that with only 50% of the arcs, you read here 99.5% of the solution objective. Remember, we are maximizing. So this is practically the best, the same optimal solution we got before. It's really, the difference is actually smaller than the 1% gap we used. And in this case, we use only 82% of the solution time. So this is quite convenient because you reduce the time and you are not affecting too much the optimal solution. And for most examples that we were able to run, that was the case. Remember, there were some examples that if we didn't do this type of heuristics, we just didn't know anything about the optimal solution. Finally, the third algorithm or heuristic is what we call the successive machine inclusion algorithm. The idea is as follows. If you have to run a model with 4 machines, that's more difficult than running 4 models, each with 1 machine, because of the combinatorial nature of the problem. So what we try to do is to exploit that and do something very similar. So we are trying to do almost as if we were running only 1 machine at a time. So for this, we first fix an order, a preferred order for the machines. And this usually the planners can do. Why? Because they are new machines, which are more profitable, more efficient, better technology. So usually the planners would prefer to do those machines rather than the other machines. Okay? So, and when they do it manually, traditionally, they start doing exactly that. They start with the best machines, and whatever they cannot put in that machine, they put it on the other machines. So we start with machine 1. We are assuming this is the best machine, solve it only there. Of course, there will be some production that still has to be taken care of, a lot of backorders, products that cannot be made on that machine, etc. Then you fix the sequence, but not the quantities for that machine, and run both machines at the same time. So you fix the delta and gammas, but you let the x to be free. Okay? So in this stage, the binary variables are associated only with the second machine, so it's not so many binary variables as if we were running the 2 machines at the same time. When you do this, basically some production could move from one machine to the other machine, and some backorders that can be taken care of. You continue doing the same until you include all the machines. At the end, you have no guarantee that this is the optimal solution, but you can run a final step where you polish the solution. You feed the solution to the optimization solver, and try to improve upon that. Without the polishing stage, these are the type of results we get. As you see, the objective function is 99.8, so basically the same solution, but only 16% of the time. I will briefly show you some of the structure of our decision support system. As you can see, it has many parts that interconnect with databases, web services, etc. The user will have a lot of interfaces where he can put all the data he needs and override whatever is not coming correctly from the SAP. He can also fix the parameters for the optimization, but if he doesn't do that, it's okay. The standard usually will work fine. And then, after he gets the solution, he can send it back to the ERP system, and the plant personnel will implement it. We started with one plant in Colombia. This year we have been doing a rollout from 5 countries, 6 plants. And we hope next year to cover all the plants in the region. The results I will present will have 2 types. The first one, the impact on the pilot plant, which has been running for more than a year, and also some comparisons between the traditional plan and the optimal plan. But the better person to give you that report will be our planner, García Millán. Oops. Hello.
Este proyecto, Buenos días. Hoy quiero compartir con ustedes nuestra experiencia con la herramienta de planeación de producción. Antes de iniciar este proyecto, la elaboración del plan de producción era una actividad dispendiosa debido a los múltiples factores que debíamos tener en cuenta y a las diferentes fuentes de datos a consultar. Los planes de producción que hemos obtenido son satisfactorios, no solo en términos de tiempo que toma el proceso de planeación, sino además en la calidad de las soluciones entregadas. Hoy puedo decir que contamos con una herramienta que nos da seguridad en el objetivo de seguir los requerimientos de nuestros mercados. El éxito de cualquier negocio es cumplir y sobrepasar las expectativas de sus clientes y consumidores, y este modelo nos ha ayudado con este objetivo. Además, puedo reportar que los ingenieros de planta han manifestado satisfacción con las secuencias de producción, porque no presentan cambios bruscos, los desperdicios son menores y los tiempos de cambio se han reducido, permitiendo una mejor utilización de la máquina. El nivel de servicio, el in-full, lo hemos logrado llevar a un 98.5% y los niveles de inventario los hemos logrado reducir considerablemente. El trabajo con el grupo de LAO ha sido altamente estimulante, puesto que hemos visto cómo transformaron múltiples veces el modelo para adecuarlo a nuestras necesidades. Vale la pena recalcar que la herramienta es fácil de utilizar y de actualizar. Es difícil imaginar que un software del mercado nos hubiera ofrecido la flexibilidad que nos ha brindado este desarrollo propio. El proceso de implementación nos ha costado mucho tiempo y mucha dedicación, no ha sido nada fácil, pero cuando uno comienza a ver los beneficios puede concluir que valió la pena. No dudaría en sugerir a los demás países que inicien con la implementación, ya que los resultados son excelentes.
Okay. Some comment about the results he was commenting about. As you can see here, during the observation period, we had an increase in service level and a decreasing level of inventory. Usually you cannot accomplish that. Probably there are many things at play here, but we believe that the model plays an important part. Also, the uptime, which is defined as the percentage of the time that the machine is up and running, has been kept quite high, even though during this period they were introducing new SKUs. That's an important part. We don't have a lot of time to comment on that, but the tool is flexible so that new SKUs can be introduced very easily. It went from 75 to 85% on average, and so it's about a 9% increase. Finally, we compared some traditional plans with the optimal plan. We did it for 4 plants and added up all the dollar figures. We forced the production to be the same between both models so that the back orders didn't come on their way because they will be the same. The most important cost will be the setup and holding cost. And we get is that even though we have an increase in 34% in setup cost, we have a decrease in 23% of holding cost. On average, there's a 12% reduction. We are not allowed to disclose the dollar figures involved, but rest assured that these pay for our efforts. So, I want to conclude our presentation highlighting the main contributions. First, we build a model to manage a production scheduling system in a very complex environment. Second, I want to comment that this was a model that served as a beachhead. It has helped us to go from being OR pushers and trying to convince people to use it to a situation where now they are calling all the people from the Operations Research and Analytics group to engage us in new additional projects. Actually, they are not very happy that I'm here right now trying to do a presentation instead of working with them. And finally, I want to emphasize that some of the heuristics and the model that we presented here can be used in many other situations, many other companies that face similar sequence-dependent setups, because the heuristics are quite general, not only for Kimberly-Clark Latin America. So I'll be happy to entertain any questions you might have.